We're going to talk about the first kind of like official wave calculations that we need to do. This is going to apply to any kind of sinusoidal or cosinal wave that we can imagine. I want us to imagine one thing here. Here's a regular. What kind of function is that? Yeah, this is a sine function. I'm adding that this axis here is a distance axis. All right, so whatever it's going to be measured in meters, right? And I'm saying that this is doing a full cycle in 2 pi what? What's my x-axis? Meters, okay, distance or meters. So in 2 pi meters, I'm doing one full cycle, whatever that means for the whatever situation it is. What can you tell me about this wave? As a property of a wave, and we're talking about distance, what could that 2 pi represent? Exactly, it represents the wavelength, all right? So here I can say that the wavelength is equal to 2 pi, right? And if my amplitude here was 1, and here, let's say, was negative 1, how would you describe this function as a mathematical, like, expression? You guys said it's a sine function. You guys said that I told you that the amplitude is 1 and minus 1, so how could you describe it as a function? Exactly, sine x. I'm going to make a distinction here. I'm going to write sine of 1x, but that's the same thing as writing sine of x, right? Right. Okay. Can I also write down that my wavelength is 2 pi over 1? I'm not really changing anything either. So far, so good? Let me draw another one here for you guys. I wrote the same kind of function, except I compressed it a bit, right? In fact, whoops, sorry. Okay. In fact, I compressed it just so that it's 2 times more squished. So now tell me a little bit about the wavelength. What can you tell me about the wavelength? Wavelength is pi. I'm going to leave a little bit of a space in front of the pi, okay? Don't put it right next to the equal sign. And how could you describe my function? Yeah, this is going to be sine of 2. So here, instead of writing pi for my wavelength, I want to write down 2 pi over 2. Same thing, right? 2 pi over 2 is the same thing as writing just pi. So now what would you have if I had lambda is equal to 2 pi over 8? What would my function look like? Not, sorry, what, not what my graph would look like, but what would the expression be? Exactly, it would be sine of ax. Okay? And that means that this variable here, a, can be expressed as a function of wavelength. Because look, if I just algebraically rearrange this expression here, what I have is a is equal to 2 pi over lambda, right? So that means I can rewrite my wave function here as sine of 2 pi over lambda times x. That makes sense? This expression here has a name. This name is called a wave number. And its variable is k. Or it's not its variable, but its symbol. It's k. So we can write that up here if you want in the title. This is k, and it's equal to 2 pi over lambda. Any questions on that? Pretty strange. Let me change things up a little bit. I'm going to erase what's on here, so just make sure you have it written down. I'm going to change one thing very fundamental. The axis on my first graph, instead of having it being distance, and I'm going to have it time. I'm going to have it to be time in seconds. So this one again is going to be time in seconds. But this doesn't change here. My expression, my calculation here doesn't change, except this won't be called lambda anymore. What will it be called? Period, exactly, because I'm having time, and one full cycle is one period. So I can change that here. So all I did was I changed this into time. Call it a period. Now my period is 2 pi over 1, and this is going to be the same thing here. It's going to be 2 pi over 2. And at the bottom here, what am I going to write? So in the end, what is this value a going to be? Yeah, 2 pi over period. And so if I were to have a function with respect to time, so if I had sine of 2 pi over period times time, because now my function is not with respect to x, it's with respect to t, right? I can write down that it's the frequency is dependent on my period. As simple as that. And we have a name for this variable as well, and that name is angular frequency. And the symbol for that is omega. It's a Greek letter, it looks like a W. And I can write that up here. And this is omega, and that's equal to 2 pi over 3. Any questions on that? Okay. Can I move on? Some of these are writing up. So I'll give you a couple more seconds. Last class, I had Fred up with me and we were playing with a slinky. I was showing you that wave can be expressed both as a function of time and as a function of distance. I remember we said you can take a snapshot and the slinky looked like a wave. And also if you looked at a particle, the particle would be oscillating up and down. Well, in fact, we can have a mathematical expression that expresses waves as a function of two different variables. That's something in math that you've not done yet. And truthfully, you're not really going to do it this year in physics, that's for sure you're not. But I want you to just see what it looks like because it is quite interesting. I want to take an example real quick, a really simple example of watering your plant. So if you water your plant and you're trying to find out how high it grows with respect to how much water you added, then you have your growth of your plant is dependent on the volume of water that you add, and this might be some function. Okay, this is like f of x. So it's g of v growth with respect to volume of water, right? But let's say you measured two variables, right? And the two variables were water and sunlight, all right? So volume of water and time exposed to sunlight, right? So now your growth is not only just dependent on volume, because that's some of your experiment is. Now your experiment is growth with respect to volume and time exposed to the sun. Okay, so you would write it like this. And this is something you might not have seen yet. It's just a way of writing a function that has two variables in it. That's what I wanted to talk about when it comes to waves. Okay? Is there any questions on just how I express this? No? That means whatever comes after an equal sign here, if it truly is dependent on volume and if it is truly dependent on time, then I should see both of those variables in my equation. You guys are used to maybe seeing f of x is equal to x squared plus 2x plus 1, right? And the only variable that you see is x. But now in this waveform function, you'll see that it's dependent on two different different variables. So here I told you consider the following string, right? This is just a string like this, and I'm saying I'm going to start moving it up and down, right? And then I'm going to freeze it in time by taking a picture. That's exactly what I was doing with Fred. And I said, look at this picture. What you see is a function. What would this axis be here? I'm impressed by my own straight line. Right? Marvel at how great that line was. If I were to make this into a graph, what would this axis be? Would this axis be distance or time? So remember, it's a string, and I took a picture of it. Distance, exactly, right? So in pictures, you don't really see time. You see just whatever is frozen in time. So at a particular time, you see the distance aspect of it. Sorry, I keep rotating this. I gotta remove my auto rotate. So this is a distance. This is what it looks like as a distance. Is it a sine function or a cosine function? Yeah, I mean, it might not be in phase or whatever, but it's still a sine function or a cosine function. Y'all agree with me? Okay, so let's do the same thing. This time, I want you to focus on this point, right? And this point, as I oscillate my whole string up and down, what is this point doing? It's moving up and down. And so if you were to graph its position with respect to time, it would look like either a sine function or a cosine function or whatever. Y'all agree with me? Okay, so now let's try to find a way to combine those two concepts together. The wave being expressed both as a function of time and as a function of distance, because that's exactly what's happening. Okay, so here I have what we call the wave form. All right, it's called wave form, and you can see here that it's the function is with respect to both distance x and time t. Right, just like I just told you guys about that a function to be with respect to two variables. Okay? And that shouldn't be unfamiliar to you. What's this variable called again? What's this expression called? We just saw it like 3 slides ago. Yeah, that would be the wave number k. And what's this expression here? Angular frequency, exactly. Okay. Sorry, the expression doesn't include t. It just includes it doesn't include this little t here. Make sure it's out of the script. No, it's really the coefficient that goes in front of the variable. Little t is the variable. The coefficient that goes in front, that's angular frequency. So I rewrote that, including my wave number and my angular frequency. So now I have, look, as a function that doesn't only depend on x, or not only on t, but both of them together. Okay? One thing I meant to ask you, and I don't mean to bring back old memories, but what does that symbol look like? Flex. Yeah, but it's not actually flex. All right. I'm glad some of you guys remember that. This is the flex is an uppercase phi. This is a lowercase phi. And what do you think it might represent in a sine or cosine function? Original y value, close. The phase, the original x value. Okay, it's the phase. All right. So here we can call this phase. For most cases, the phase is going to be 0. Okay, because you choose when to start your experiment. And we'll do some examples where it's not 0. But if I don't tell you what the phase is, just go ahead and make it 0. It'll make your calculations a lot easier. Okay. So I'm going to write down here most of the time 0. what would the phase be measured in? Distance and time? Well, I kind of like that answer, but it's not the correct answer. When you take a cosine of something, what do you put in the brackets of a cosine of something? Angle can be expressed in 2 units. Which are the 2 units? Radians and degrees, okay? So that means that this expression, 2 pi over lambda times x, has to be expressed in radians or degrees. This has to be expressed in radians and degrees. And so does the phase angle has to be expressed in radians or degrees. Now let's just check that. Look, 2 pi, that's in radians, divided by meters, multiplied by meters, right? So the meters, they would cancel out, and you're left with radian. Here you have 2 pi over a time multiplied by a time. The time cancels out, you're left with radian. And here your phase angle is also in radian. Okay? So here you've seen it's the same form that I showed you just now, except I factored out the 2 pi. And it's just a different way for you guys to see it look differently. Okay? I want to point your attention to this here. That by convention, we write down first of all, what can you tell me is a difference? What do you notice is a difference? Spot the difference between these two equations. Yeah, so here is a minus and here is a plus. So here, this is a wave. We call it when it's a minus here, we call this a wave moving towards the right. And by convention, when it's a plus, we call this a wave moving towards the left. Okay? If I don't specify, and I'm just talking about, let's say, a flag waving on a pole, then you choose. It's not going to make a difference in the type. Any questions? Yeah. What's y? So let's say I have a function, a wave function where I have it with respect to distance, right? So I took a picture of my slinky, right? And so on this axis, it's distance. On this axis is also distance. We call this one the y distance, right? And let's say it was we're looking at just a particle, and that particle is oscillating, right? Where is it oscillating? It's oscillating in the y direction. So that's why we'll always just call this y, okay? And it would be measured in which unit? And that makes sense, right? If I did the cosine of whatever angle, what's the unit of the cosine of an angle? Does it have a unit? No, cosine of 2 pi is what? What's the cosine of 2 pi? 1, right? There's no unit associated. And what's the unit of amplitude? Meters, right? Because it's how up and down I perturb my wave. So then it makes sense that y is also a unit. Yeah, Max. Good question. So the amplitude is from 0 to up there. Okay? It's called the equilibrium line. Okay. Let's do one example. I'll give you guys, let's say, 5 minutes. Yeah, take 5 minutes, do this example. I'll come around and see if there's any help. Please work at it with people around you. I like talking. Nazir, you can say how your class went. I think one big issue with that is our classroom. I think the desks all facing the front is not a good setup. So I don't have the class for all of the big offices. I want to remind you and get you guys started off on this a little bit. I want to remind you that speed of a wave can be as, or I wrote c, but that's just the speed of light. But the speed of a wave can be expressed as the product of frequency and wavelength. I want to remind you that frequency is 1 over the period, right? And I also want to remind you that you can write a wave function as a waveform as a function of distance and time. So that would have been kx minus omega t minus the phase angle, and that you can express as a f of x t. Even in the phase infinity. Try to identify in the question what they're doing. This one's very explicit. They're telling you the speed is that, the amplitude is that, the wavelength is that. Sometimes it'll be a bit more difficult. We're just finding other conditions to do this. This is going to be very, very difficult. Anyone find the frequency? Max, what'd you get? 25? Lara, you agreed? You agree? What are the units? Hertz, good. Am I going to have to complete it? 0.04? You want to tell me the unit? Seconds, very good. You have an answer? Right? Once you're done, go take a break, come back and come back up. Well, come back to life. So since at t is equal to 0, the end of the string is at 0. So that means it starts here. So that's not a function. So it's a negative sign function, right? So you start writing cosine, you write negative. Yeah, exactly. You have to do that unless you want to do it like I want to draw your attention to this y value. So it says that time is equal to 0 and at x is equal to 0, the y value is 0. So that means that the origin is going to be on the x and y intersection, right? And then it says that the wave moves downwards, right? So if that were the case, if I have my function like this, and then it starts going downwards, then it's going to go up. And therefore, it doesn't have a cosine shape. What kind of shape is it? A negative sign, not a regular sign, but a negative sign. So the sign would go upwards first, right? So this would be a negative sign. This would be sign. When you're writing your equation for part B here, when you're writing your equation, make sure that you keep that into account. If you don't, if you use a cosine, then you're going to get a phase angle, right? And you don't want to deal with that mess. So, right. Yeah. The thing about the wave of making all of it's photonic is concerned. So in this case, if you wrote negative sign, it would be 0. Let's say you wrote cosine, right? Cosine, let's start here. say phase change from here to here. Well, forget about that. Let's just talk about in terms of radians. Yeah. So how many radians separates the peak here to this? So this is 2 pi. This is 1 pi. This is half pi. So if you wanted to convert a cosine into a negative sign, you have to do a phase change by half a pi. So your phase change here is going to be pi over 2. Yeah? Let's say 1205, guys, okay? 1105. 1105. What's it? You need to find out how much Where'd you get it? Minus 0.049 units. What's the question? Find the y displacement. What's displacement needed? Is everyone in agreement with that number? Did you get that one?
I didn't touch it.
Valerie, you got that? Okay, good. 1105. I'll be gone at that point. was 0.049, I think. Am I right in that? 0.049? Okay, let's get started then. I want you guys to open up PowerPoint number 3. We're going to do something called simple harmonic motion. And if you look at it up in textbooks or online resources, it's oftentimes abbreviated as SHM, right? So simple harmonic motion. And that's basically any physical thing that's behaving like a repetitive oscillating motion. So the example that I have up on the board is a mass spring system. So imagine that a black block here is connected to a spring on both sides, and that spring is pulling it back and forth. So one spring pulls it, creating potential energy in the other spring, and that other spring pulls it back. And theoretically, if there's no friction, there's no energy loss in the system, this will go on forever. And the same thing with our pendulum here, and that's what you guys did in your lab this morning, was simple harmonic motion. Look at it oscillating back and forth, back and forth. Think of this as kind of like a grandfather clock or pendulum. Another really classic example is if you hang from the ceiling, let's say a spring, and then hang a mass from it, and then you pull that mass and it bobs up and down. I think you guys did an experiment with springs and masses when you were in Canada. Not on simple harmonic motion, of course, but I remember you had to, if you remember, you had to measure the extension of the spring, twist it off, and then you couldn't get it to be stable because that thing kept bouncing up and down. The reason why that was bouncing up and down is because it was undergoing something called simple harmonic. We're going to be able to describe all that. This is a topic, this is the main topic on the quiz that's going to be on Tuesday for you guys. And it's the first kind of like main subject in this course. It's not very long and it's definitely not difficult. It's just one of those things that every waves course will teach you guys. All right, so let's start. So we'll be able to define simple harmonic motion, use some examples, and make some calculations. That's pretty much the goal of this. So I want you guys to imagine that I have a spring attached to a mat, and you guys played with the slinky the other day, and a slinky, if you held it up to your hand, held it in your hand like this, flat, it was in a fully compressed or decompressed state. Fully compressed state. You hold a slinky like this, it's fully compressed. You actually can't compress it anymore. In this experiment, right, the spring can't be like that. This kind of spring has to be both able to be compressed and extended. Okay? So that's the kind of spring that we have. And at equilibrium, right, it's going to rest on this 0 point. So we're going to call that the equilibrium point. All right? And it hasn't moved or anything. This is like if I haven't even touched it and I'm just leaving it there, where is it going to want to be naturally? I have to ignore friction in this, all right? Because we're going to go in an ideal world. We'll do friction on Monday when you guys get some meet. And so now if you were to pull this, if I were to pull this mat towards the right, then I'm now decompressing the spring with a distance of x, right? And then you can use Hooke's law to determine the force if you want to. You can use Hooke's law also to determine the amount of energy. And that's going to, when I let it go, what's going to happen to that mass? It's going to go in that direction, right? And then it's going to go in that direction. What happens when it reaches this point? It's going to go back because now there's more potential energy. Right now, instead of it being decompressed potential energy, it's going to be compressed potential energy. And the difference between those two is nothing. All right, you're calculating the same way. It's 1/2 kx squared for the energy of a spring. So it's going to be full potential energy, full potential energy, full potential energy, and it's going to oscillate back and forth until forever if there's no friction. What about as it's passing the middle? What's going to be it's got no force there because that's the equilibrium. So what kind of energy does it have here? Yeah, here it's going to have maximum kinetic energy. Okay, so you have to understand that it's going from maximum elastic energy to maximum kinetic energy back to maximum elastic energy, and this is going to oscillate back and forth forever. Okay? And the idea is to measure the period of this because it's a oscillating function. The expression for the period is given right here. And it's interesting because there's one variable in there, there's one variable that's not there, an important one. Which important variable it does not determine my period? Think of you doing this experiment, right? And something very crucial with this experiment doesn't actually affect the period. What's that? What do you think it is? The string constant's there, okay. What do you mean by the distance? Exactly, right? So I can pull this all the way over here and let go, or I can just pull it over here and let go. And regardless of how much I pull it, the period is going to be the same. Now that's pretty substantial. Okay? So amplitude is not a variable. So far, so good? There's one thing I want to talk about, and that's how to describe its position with respect to time, how to describe its velocity, and how to describe its acceleration with respect to time. All right, and position is quite easy. It's an oscillating function, right? So it's going to be some kind of cosine or sine function. If I were to pull it to some maximum, and then let go, right? Am I starting at the maximum or am I starting at the zero? I'm starting at the maximum. And I'm assuming that, let's say this is, ooh, on this side, let's call this positive x, and on this side, let's call this negative x, right? Is it starting on the positive side or the negative side? Okay, so it's starting at its positive maximum and then going towards the negative. So if I have to describe this in a cosine or a sine function, which one would I choose? I would choose a cosine function. So let's do that. Let's call, I'm not going to call it p of t. I'm going to call it x of t because that's what all the textbooks use. But it's the same thing. Position with respect to time, the distance with respect to time. It's the same thing. If I were to describe it, I would say that it has some amplitude multiplied by cosine. And this is an object that's oscillating with respect to time. So I'm not even going to worry about distance. I'm not talking about the waveform, that differential equation that I showed you in the last PowerPoint. I'm just talking about with respect to time only. So what's the coefficient that goes in front of the variable, and what's the variable? I'm talking about time. So which one was it? It was what? I heard something. Which way? Angular frequency, exactly, because it's with respect to time. And it's angular frequency multiplied by, what's the variable? Time. Okay, great. And that's pretty much how I describe my my function, right? It's as simple as that. And we have to remember that here I have 2 pi times square root of m over k. You have to go back to last class now. You have to remember that, okay, so t is equal to 1 over f. So that means that f is equal to 1 over 2 pi square root of k over m. Right? All I did was the reciprocal of this. The reciprocal of this is frequency. Right? Everyone followed there. And we have to remember that 2 pi f is angular frequency. So I'm going to write that up here just to remind you guys. 2 pi f is angular frequency. You guys remember that? Now that I've said it, you guys remember that? I hope so. So if that were the case, I can bring my 2 pi up to the front here, and then I would have 2 pi f is equal to the square root of k over m. And oh wait, 2 pi f, that's just an angular frequency. So my angular frequency is just the square root of k over m. And I can plug that into my cosine function on the next page. All right? So here, I can write down that omega is equal to the square root of k over m. Yeah, I should have mentioned that actually. So here k is spring constant, and it's measured in newtons per meter. And m is for mass measured in kilograms. Okay, back to this. We have an expression for position with respect to time. How would we find the expression for velocity with respect to time? What's the relationship between velocity and position? Position divided by time. That's if it's a linear function, but if it's any other function, how would you do it? You do the derivative. And I'm going to do it. I'm not expecting you guys to do it, but let's do it together. So velocity is the same thing as the derivative of position. You guys remember what the derivative of a cosine function is? Minus sine, exactly. And there's a variable, there's a coefficient inside, so I have to do the multiplied by the derivative of the inside of the bracket. So it'd be negative a omega sine. So far, so good? Again, I'm not going to ask you guys to do this. I'm only just showing it to you to see, show you where the equations are coming from. How about acceleration with respect to time? What's the relationship? Derivative of velocity, exactly, or the double derivative of distance. Right? And what's the derivative of a sine function? Cosine. What's the derivative of a negative sine function? Negative cosine function. Don't forget, multiply by the derivative on the inside. So now I'm going to have negative a omega squared cosine of omega t. So far, so good? You can go ahead and put a big square around this because you're going to need to know these equations. I'll give them to you on a test, or at least I would give them to you. That's to make sure with Lee. I don't see why people would disagree with him. Yeah, it does. But he taught you guys linear. You don't get formulas in linear algebra. This is physics. You got a sheet, no? That's amazing. This is physics is different. You get formulas. I was against the idea of him having a formula sheet at all in math. I was like, formula sheet in math? There's no formulas in math. Anyway, let's apply this to a different thing, right? So before we're doing an oscillating spring that was horizontal, now we're doing an oscillating spring that's vertical. You know what? It's exactly the same thing, right? So omega is equal to K over M. Same thing as before. The position, the velocity, the acceleration graph, exactly the same thing. What strikes you here? Like we said that how much you pull it down doesn't affect the angular frequency. But here's another thing. Now we're dealing with an extra force. Which force are we dealing with extra now? Gravity, right? But look at that. There's no gravity in the equation either. If you did this experiment on the planet Jupiter, you would have the same frequency because it's only dependent on, sorry, the period, either frequency or the angular frequency, is only dependent on the spring and on the mass. Okay? So G is not a variable. Amazing. You guys know what behaves like a mass in a spring? Something that's very, very common. In fact, there are so many of them that it's impossible to count. Is that? Atoms, exactly, right? So when you have covalent bonds, they actually are oscillating like a spring, and the covalent bond acts like a spring. Ugh. Any questions? Yeah? Oh, there's going to be a lot of text that's going to show up, so it's going to be hard to know. One thing that I never mentioned to you guys, everything on the text here is, you know this already. I'm not too worried about that. But I want to talk about just this term crest and this term trough. So when when we're describing a sine function or a cosine function, we call the maximum, we call that a crest or a peak, right? Peak. And we call the minimums, we call that as troughs. It's pronounced trough, like cough, and it's written like that. Those are not very scientific terms. Those are just layman's terms. Scientifically, we call them, or mathematically, we call them maxes and minimums, or local maxes and local minimums. But you might hear textbooks use these terms. I don't want you to get confused about what they are. Okay? So peaks, crests, troughs, just be familiar with those terms. Okay? If I had to graph the energy here of my system, at some maximum energy level here, let me go back here. There's your positive x direction. There's your negative x direction. That's your equilibrium. And this spring is oscillating up and down, all right? This distance and this distance, although it might not show it on this diagram, is supposed to be equal, all right? So it's going to be the amplitude in the negative direction or the amplitude in the positive direction, right? And the most this spring is going to be stretched is going to be by a distance of whatever I indicated here, x, which is really just the amplitude, right? And when I pull it to its maximum, right, or to just before I let it go, that's the point where it has the most kind of which kind of energy? Elastic potential energy. All right, so up here, I'm going to have my potential ES equal to 1/2 K A squared. Okay, and I said A because it might as well just be A because that's the amplitude. That's the maximum amount. And so then as it gets closer to the equilibrium, it's going to decrease. Right? And then as it goes in the negative direction, it's also going to increase. Like that. And over here, what's the amount of energy that it has at the total other side? That would be the same thing. It's all that energy came back to being elastic potential energy. Well, that's pretty great. And at here, it's got no elastic energy, and that makes sense because it's back in the middle, right? So over here, it represents the mass being down here. Then as it gets closer to equilibrium, it's going to have no elastic energy because the spring is neither compressed nor stretched. And then it's going to compress. So now the mass is up here and your spring is compressed and you have more elastic energy. Yep. Yeah, absolutely. So that's my next step. So if I were to just change colors here, and I were to draw on the same graph kinetic energy with respect to the distance from the equilibrium, what would it look like? It would be exactly the opposite, yeah. So it would look like this. And that makes sense for the zeros here. It makes sense. Just think about it for a second. I want you guys to say, if this is the positive direction, downwards is the positive direction, right? On its way down, its velocity is positive or negative? Positive, and then it goes, okay, and then reaches the maximum, and then it comes back up. And so now the velocity is positive or negative? Negative. So what's between positive and negative velocity? Zero velocity, and that makes sense. And if kinetic energy, what's the expression for kinetic energy again? 1/2 mv squared. If v is zero, then you have no kinetic energy, right? So here you have no kinetic energy, so Ke is equal to 0. Here, Ke is equal to 0. And what's the energy here? What's the maximum kinetic energy equal to? It's 1/2 mv max squared, but quantitatively, it's exactly equal to what if it's a perfect system? Yeah, it would be equal to the maximum elastic energy, quantitatively. If I were to take this value here, if I just took a random position anywhere along, not at the special times, I call these the special times, but there is a whole bunch, the mass does a whole bunch of things in between the special times, right? This object has a certain amount of elastic energy and a certain amount of, let me change colors actually. Okay, I'm just going to write the blue one here. It's got a certain amount of kinetic energy and a certain amount of potential energy, what can you say about the sum of these two? Yeah, exactly. So no matter what, the total energy at any time in this system is always going to be equal to the maximum energy that you put into the system. That's the law of conservation of energy. Yeah, no. A is the amplitude. So how far I stretch the spring in meters. So here, if I were to give it an expression, here I would say it's 1/2 kx squared, and oh, it's not working. Okay, I'll just do it in red. And here, it's going to be 1/2 mv squared, and you can say that 1/2 mv squared plus 1/2 kx squared is going to be equal to 1/2 ka squared at any point. Any questions on that? Here is how to prove for you guys, but I'm going to skip over it with time in my interest. You don't need to know it anyways. It was more out of interest, so I'm going to skip over it. Hold on, give me a second. My PowerPoint seems to have locked up a bit. All right, so that's exactly what I was just talking to you guys about. So you can see here at equilibrium, it's got the maximum amount of kinetic energy, and all that energy gets converted to potential. Here it's going to be back at kinetic. Here is going to be potential, kinetic. Here, potential, kinetic, potential. Okay, it just repeats over and over again. Always the same 2 joules. If I take it at some point here, whatever it was, the sum of the two types of energy would be equal to 2 joules. Yeah, exactly. And I wrote down this again. Don't forget it, okay? So not only is this the period for the motion, it's also the period for the energy. All right. So at this point, you have 2 joules, right? How long is it going to take for it to have 2 joules again? Well, you can figure that out by using the period here. Okay. You guys just did a pendulum experiment, and that is, yeah, sorry. Yeah. Ah, I see what you mean. If I were to come here, yeah, because the values are squared, it would look like if you were to take a sine function and did a square and then square root it. Yeah. So it looks like either W's or M's. So like if I took this function and did an absolute value for it because I squared it, it would look like that part's positive, so it's always positive, and everything that's negative is going to be positive. So it's going to look like this. Yeah. What's that? Yeah. It's kind of like an absolute value function, but it's not really because it's just squared. That was a good question. Let's talk about pendulums real quick, right? And I'm gonna have you guys do some problems. In a pendulum, um, you would take this, let go, and then it would sway back and forth. If there was no air resistance, no friction, nothing, it would go on forever. You can measure the frequency of that or the period of that. You guys just did it, right? But there was a way to calculate it, and you'll be surprised at what actually is a variable in it. right? Because you guys are doing it right now and you're like, this one doesn't affect the period. And I'm going to come back to this slide in a second. If I were to give it to you, the period is actually only given, is only dependent on the length of the string and the acceleration of gravity. That's pretty remarkable because that means that the mass that I hung at the bottom of that did not affect my period, right? And what else didn't affect my period? Sounds weird saying that. Yeah, yeah, the amplitude, right? So no matter how high I let that thing go, I should have gotten the same exact period. No matter what mass I hung from it, I should have gotten the exact same period, right? What would have affected it if it was shorter length, or if I had, if I was on a different planet, which you guys aren't from different planets. I mean, I guess metaphorically you might be from a different planet, but physically you're from here. And so here are those equations, now this time for a pendulum. I think from this, I'll just go. Is everyone done with this? Everyone's okay? Any questions? Okay. Real quick, a damped oscillation, which is what we're going to do on Monday, kind of looks like this. It's the exact same thing, except the amplitude dies with respect to time. What I just want you guys to notice is if I had this as a function, this here is an expression. You have an expression, your amplitude is differential based on time. So your amplitude is not always going to be the same, like if it were not damped situation, but it would change with time. But you don't have to worry about that now. We'll deal with it on Monday, but just keep that in mind. And lastly, I wanted to show you guys that circular motion. Circular motion. So imagine this is a mass on a string that's being turned on itself. You guys might have done that in mechanics with Mr. Wakarsky. A spring oscillating back and forth are both simple harmonic motion. And they have the same exact idea, principle, that there's this interplay between kinetic and potential energy. Right? The same thing there. That's all I need you guys to know from that. I don't need you guys to know about centripetal or centrifugal force or anything like that. You've been tested on that in mechanics. Okay. I have some examples, but before I do that, I want to just bring your attention to one thing. I skipped over the proof of this, and the reason for that is because I want you guys in the bonus assignment, if you're interested, to show me the proof of the angular frequency of a pendulum. Okay, so I'll give you guys until next class to do that. You don't have to do it right now. You can do it in groups of 2, not more. If you're interested in that, come and see me, and I'll show you the proof for the spring, and that way you can use that knowledge to be able to prove the pendulum. Only if you're interested. I'm never going to ask you on a test to prove anything, not to prove these things, maybe something else, but I'm not going to ask you to prove these things. This is really more for your interest. So if you're interested in doing that, please come and see me and I'll explain it to you, and it'll be due next class. For now, there's these examples that I want you guys to practice with. Go ahead and do them in groups, and once you're done, you can leave. Okay? Thank you.